in this section, we'll learn about buffers, which are going to be a special type of solution that contains a weak acid plus its conjugate base. And so we'll have both of them present in solution. And so we will have a common ion, right? The conjugate base will be your common ion, whatever it is. If it's, for example, acetate, that's going to disrupt your equilibrium, right? What's important about buffers is that by having a weak acid and a conjugate base together, we'll see that by adding a certain amount of strong acid or weak acid, we won't really change the pH of our solution. That's the benefit of this. And this is why this is biologically relevant, because as we've seen earlier, we need to really keep our blood pH quite exact, 7.40, because we see that any, even minor deviation from that leads to sickness and death. And so, as we exercise and all that, we're producing more acid. Our body has to have a way of absorbing that acid without changing the pH. And our body uses three primary buffer systems. We have the proteins within the plasma, we have the bicarbonate, which is our main one, and then we have the phosphate buffer system. So we have all sorts of different buffers that are made of a weak acid and its conjugate base. So let's see what happens. If we have a weak acid and its conjugate base present in solution, say acetic acid and acetate, we'll see that if we add a strong base, so adding a strong base to something that has acetic acid, will react that acetic acid to form water plus acetate. So we have taken a weak acid and a strong base, whatever that might be, strong base that we're adding in, and we're neutralizing it. We're producing acetate, which is a weak base. So in essence, we are taking a strong base that is added to our system, and we're converting it into a weak base. So the pOH, or pH, either one, of your strong base will be extreme, right? It'll be, if you're looking at pH, it'll be very high. But the pH of a solution of acetate would be kind of only a little bit high by comparison. And on the other hand, if we take our acetate solution, acetate part of the solution, and we go ahead and react that with a strong acid, well, guess what? We're going to make our negligible base and a weak acid. Oops, we'll make our acetic acid. So buffers resist pH change. They take incoming strong acid, and effectively turn it into a weak acid by reacting the conjugate base away. And on the other side of things, if they have incoming strong base, they will turn that into a weak base. Your weak acid will react with your strong base, producing your weak conjugate base. And so overall, they resist the pH change. In either case of addition of acid or base, your buffer system will prevent it from happening. And if we really wanted to look at this sort of fun stuff, if we wanted to put our Ka together along with our understanding of Kw, we can go ahead and write it out. Remember that Ka is H plus times A minus over HA, right? That is Ka as the equilibrium expression. There we go. Can't think of the words right now. If we wanted to solve this for pH, remember pH being the negative log of H plus, we can do that. If we go ahead and take the P of everything here, we can do that. But first, let's go ahead and move everything off to the sides. Let's have H plus by itself so that when we solve it, we'll solve for pH. So H plus would be equal to Ka times HA over A minus. Right? So, ta-da, we've got that. We've moved it over. We've multiplied by the reciprocal. Once we do that, if we take the negative log of both sides, negative log of H plus is negative log of Ka. Remember that if you have logarithms for things that are multiplied or divided, those become addition and subtraction, right, for logarithms. Like log xy, x times y, is log x plus log y. So you can kind of distribute the logarithm there. We could say that it's plus minus log of HA, since HA times Ka, and we're doing minus log to everything. And then we're going to minus log A minus, right? Because A minus is on the bottom, so we're subtracting the log of that. And since we're doing negative log of everything, we're going to just keep our negatives there. So pH, therefore, would be pKa, which is, again, something we've seen before. We've got we've got minus log of HA plus log of A minus. And if we really wanted, remember that we can combine, therefore, if we know the signs of the logs, we can combine those together if we were so inclined. So just like we separated them out before, we can say plus log of A minus over HA and put those all in one big term. And so you don't have to worry about the derivation of it, but that's how we come up with this equation. And it's a way for us to say, okay, well, how much of the conjugate base do we have here? And what about the weak acid? And then we have its pKa. And that'll be able to tell us the pH of the solution, which is pretty cool. So we'll leave it here for now, because I want to take a break here. This is the equation that we're going to be using. It's called the Henderson Hasselbalch equation, which is just a rearrangement of our Ka equilibrium. And so we'll take a look at how to use this in our next video, as well as figuring out how the conjugate base and weak acid concentrations change in the course of incoming acid or base.